Okay, Andreas, you need to get your food. So. Okay, so continue to enjoy your food. In the interest of time, I just thought we'll get moving with the program here and uh, give you a chance to really interact with our fantastic officers as well as all the activities that are happening within the South Texas section. So just as a point of introduction, I'm Ramanan Krishnamurthy. I'm the chair for STS-AIChE for 2021. This is our first face-to-face meeting in 18 months, and so thank you all for being here. I want to call out one person who has been instrumental in keeping our organization going and being active, and that's Mark. I don't see Mark. Where did he vanish? Mark Harkness. I warned him not to leave. I think he took that as clue to leave. But he was the chair last year when we had to pivot from going from face-to-face meetings to online meetings. We never got a chance to thank him for all the work that he's done. He's just been an incredible chair and past chair of this organization, and really deserves a lot of credit for what we're doing. So big thanks to Mark and to all the officers here. So I have a brief agenda today. We're going to talk a little bit about what happens in the rest of the fall. I want to talk about what we've done with the collaboration with AIChE and TEEP in terms of this conference, the SPTC, and give you an update on some of the elections as well as awards. So where are we? Our next dinner meeting will be on November the 4th, I believe. And that's going to be, the pre-dinner is going to be a workshop on the reuse and recycling of wind turbine blades. Ebhard Luki from Luki Consulting will be our speaker, and then followed by a 7 to 8 p.m. dinner meeting on engineering sustainable solutions with Greentown Labs and a startup company in Greentown Labs being the primary speakers there. So really bringing that entrepreneurial and innovation mindset of where the field is moving to STS. In December, we will be doing a holiday get-together, not a technical program, and I certainly invite you all to join us for that event. In terms of the SPTC conference, this is really what has brought us all together here for an October meeting on September 30th. So this will be normally our October meeting, but we're doing it on September 30th because of the SPTC. And really, big kudos to many of our colleagues here, Ian Glasgow, Alan, and Virginia. They have been truly incredible volunteers from the STS side, working with the AIChE group, with Todd, Justin, and Stephanie, to really deliver an incredible program, not just this year, but also last year. They went virtual, they delivered an incredible program, and this year, they've come back and done even better. So thank you so much, Alan, and please accept our congratulations for a fantastic program. So in terms of what we've done for elections, I want to recognize Andreas Matsakos, who's here. Andreas, please stand up and please be recognized. He is the chair-elect for 2022. And he will continue in 2023 as chair, and 2024 as past. So it's a 3-year term, and certainly somebody that I greatly value for having volunteered to do this job. You're all going to be in great hands next year, right? We've got Julie, who is here, Julie White, who is our chair-elect this year and going to be next year's chair. Julie, please stand up and be recognized. She's an incredible force, and you're going to see how that plays out next year with the program. So we're all looking forward to that, Julie, and thank you so much for being a real great volunteer and partner in getting all of this done. Want to thank Eureka. Without Eureka, we would not be here. So Eureka, thank you for all that you do. If you see good things happening with this program, it's all Eureka, okay? I will take all the blame for anything that goes wrong, so, and I deserve it. So with that said, I want to alert you to the fact that we will be having elections for the other officers that will be coming up, and that will be in your mailboxes as soon as Mark and the group can find the full slate of candidates. Will get you the elections to take forward. I want to now shift gears and talk about some recognitions for other things that have happened. One of the big events that happened in the last couple of months was the Offshore Technology Conference. It was held August 16th through 19th at the NRG Center, and STS has a big role to play at that conference. And we do this with the help of volunteers. And so Tom Mann, I think you need to take great credit for what you do in terms of organizing everybody there. And this seems to have a mind of its own to try and go ahead. So let me sort of make sure that we do this right. Want to make sure we recognize all the volunteers. David, Aaron's here. So Aaron, thank you so much for what you've done. James Smith, John Middleton, Gianni, David Solarski. David's here. So David, thank you for your years of service to the section. Catherine, Carlton, Michael, James Mann, Israel, Donald, Judy, and Mark. So thank you. We also are here, the sort of a big part of this October meeting is the awards. And so I want to give a special thanks to Tom Mann for putting that group together and organizing that group of Shell volunteers for all the work that they do. The awards committee is nominally managed by Tom, but the chair for it is Matt Christensen, and the co-chair is Ryan Stevens, both of Shell. And they do a yeoman's work in sort of identifying and really going through a pretty large selection of papers that get submitted each year. Tom, from this point onwards, I want to hand it off to you to really take over the rest of the emceeing for this part of the awards. Julie, can you join me up front? And so that way we can make sure we get the awards to the right people. So a bunch of volunteers from Shell who come and work hard and deliver the program. So I will hand off to Tom.
Okay. The South Texas section, the best papers judging competition received 4 applied papers, 4 fundamental papers, and no in-practice papers. The team was chaired by Matt Christensen and Ryan Stevens serving as co-chair. Both these guys are from Shell, as are the rest of the people that are listed up here. I'm not going to go. How do you get this thing to move up? No, this.
Just move it down. That's all.
I don't use these things.
I know. I can help you.
Okay. On behalf of the South Texas Section AICHE, I wish to extend the STS-AICHE's deepest appreciation and thanks for contributing your time, talents, efforts, and a job well done. The STS-AICHE back. Best applied paper was titled Compression Stiffening of Fibrous Networks with Stiff Inclusions, published in Proceedings of the National Academy of Sciences, Volume 117, 17th August 2020, pages 21,037, 21,044, and was authored by Jordan L. Shivers, Jing Sheng Feng, Ann S. Van Oosten, Herbert Levine, Paul A. Janemy, and Fred C. McIntosh. Will the recipients please come forward to receive their awards? Congratulations. The 2020 Best South Texas Section Best Fundamental Paper was titled Critical Role of Confinement in NMR Structural Relaxation and Diffusion of Normal Heptane in a Polymer Matrix Revealed by MD Simulations, published in the Journal of, published in the Journal of Physical Chemistry B, 2020, Volume 124, April 8, 2020, pages 3,801, 3,810, and was authored by Arjun I'm going to give this a try. Paramabathu, Philip M. Singer, George T. Harasaki, Walter G. Chapman, and Dilip S. Stangi. Will the recipients please come forward to receive their awards? Congratulations. That is the trickiest. The 2020 South Texas Section AIChE Special Service Award just a minute. I got it. I give up.
Sorry about that. There you go.
Is Alan P. Rossiter. He has been instrumental in the direction and arranging of the Southwest Process Technology Conference, and the South Texas section wishes to recognize him for his efforts over the years. Congratulations, Alan. The hell with it. Okay. It's got a mind of its own.
It's got a mind of its own, so let's just not worry about it.
Babak 2020 South Texas Section AIChE Outstanding Young Professional Award recipient. Babak Rafinia is a BS from Shiraz University, Iran, and an MSCHE from Lamar University. An AIChE senior member, he has been employed by AMAX process tower internal since 2014, is currently a mass transfer technology manager. Barack has served the South Texas section as a member of the executive committee that's the continuing education from 2019 to 2020, organized the monthly dinner meeting technical workshops, and also collaborate with the chair and inviting dinner speakers. He also served as a judge on several SPT Best Technical Presentation Award committees. Barack has also presented technical seminars on distillation and separation for Louisiana and Texas AIChE local chapters and YP groups. Barack has served as the secretary of the AIChE Management Division from 2019 to 2020 and currently serves as the director of the AIChE Management Division from 2021 to 2023. He is a recipient of the 2020 AIChE's 35 Under 35 Award for Leadership. Barack is a member of the Houston Gas Processors Association, HGPA, and AMAX member and technical representative at FRI, or Fractionation Research Incorporated. Barack already got his award.
Okay, so as you all are waiting for your desserts, there's actually dessert at the back of the room. So please do feel free to go and get that before we get started with the big dinner presentation. So there's dessert, coffee, and tea at the back for those of you interested. But now that, pardon? Yes, please. So now is a good time to embarrass Mark. So Mark, you try to escape this, so have you back here. I wanted to thank you for everything that you've done for the South Texas section for the last couple years.
Thank you.
Truly yeoman service, and we said all good things about you when you were gone, but thank you.
I'm sure you did. Thank you. I don't need any help embarrassing myself, but thank you for the offer. Just wanted to mention a couple things about the elections. We did have our election for chair-elect, and our chair-elect for 2020 is here this evening, Andreas. Oh, have you already? Okay. We also have elections for three other positions coming up. Secretary, in the position 2 on the executive committee, in position 4. We have nominees for secretary in position 2. We are looking for nominees for position 4, which is a human resources officer for the executive committee. If anyone has any interest or may know of someone that has any interest, please let me know. Would certainly appreciate that. So anyway, sorry to interrupt.
Thank you so much, Mark.
All right.
Appreciate it. So without further ado, let me introduce our dinner speaker. Kristen Jenkins is a professional engineer. She is a VP for Sustainability Solutions for OLI Systems, and she's located in Atlanta. Kristen is as I mentioned, is the Vice President for Sustainability Solutions. She has her bachelor's degree from the University of Tennessee and her master's from Virginia Tech. And her PE is in the state of North Carolina. And OLI as a sponsor of SPTC, and also as a big part of the ecosystem in Houston, is certainly advancing a lot of methodologies in the area of sustainability. And I want to give a special call out to OLI for all that they're doing, but also give you a chance to listen to Kristen's presentation this evening, specifically in the area of PFAS. These are these forever chemicals that are starting to become significant challenges in all of the industry, and specifically the area of industrial wastewater. That, without further ado, Kristen, thank you so much for doing this.
Thank you very much. I'm excited to be here. Can folks in the back hear me okay? Maybe wave or not? It's okay. Okay, great. Thank you. Here we go. So as far as my talk tonight, first I'll go through an introduction to OLI systems and what we do, and then I will get into industrial water treatment. That's, as Ramanan mentioned, that's my background and area of expertise. So I'll give a little bit of a background on industrial water and some of the drivers for treatment, and then get into a section on emerging contaminants, including PFAS. So if you haven't heard of PFAS before, hopefully when you leave here tonight, you'll understand what it is and why it's an issue. And then I'll get into some PFAS treatment solutions. I've done quite a bit of study and experimental and design work around PFAS treatment. And then I'll get into some modeling applications and some things that OLI is doing in the water treatment space. And then I'll end with some time for questions. There's a little bit of a delay with the slides, so I apologize. So water chemistry impacts industrial process performance in a number of areas. It can have specific impact in many industrial processes, and we have expertise in software applications in all the industries shown here: oil and gas, chemicals, metals and mining, power generation, and water treatment. So mineral scaling is one example, a calculation that we can do that affects productivity and operational efficiency. Corrosion can impact reliability, and then other reactions can impact air and water quality as well. So understanding the electrolyte chemistry and water behavior helps to design and operate equipment and processes more effectively and efficiently. So OLI has a deep chemistry expertise for industrial water and wastewater treatment. We have experience over a broad range of source waters. A few of those are shown here, like produced water, mining water, industrial, power and utilities, as well as pulp and paper. And we have unique capabilities to accurately simulate these processes and predict thermophysical transport properties, as well as surface tension and mineral scaling. We have a proven water chemistry process modeling leadership. Our electrolyte chemistry database covers 80 elements of the periodic table and 6,000 species. We have over 3 decades of R&D innovation experience and have invested over $150 million in developing the OLI platform. Over a third of our company are PhDs. So we're also actively engaged in industry standard groups, and I'll talk a little bit about those in a couple of slides. So we have global industry leading clients and technology partners. This slide shows some of our global partners across a range of industries. We also have technology partners that are shown in this slide. So the OLI chemistry engine can be a part of Aviva, AspenTech, PSE to name a few. We're also part of the NOWI Alliance, which is the National Alliance for Water Innovation, and are working with them to develop water treatment simulation software and to enhance scale inhibition modeling. So this year is our 50th anniversary. So we have 5 decades of electrolyte R&D innovation and collaboration. We have a history of collaborating with research organizations, including the Department of Energy, various national labs. We've also participated in several joint industry partnerships with leading operators and suppliers in both the oil and gas and chemicals industry. We have the most comprehensive water chemistry solutions portfolio and can provide a range of services from consulting and research to support. We offer cloud software as well as several Windows software applications. Thank you. And I'll get later in the presentation, I'll get into some examples of these software. It includes OLI Studio, which does a single point equilibrium analysis or survey calculations, and then OLI Flowsheet ESP, which allows you to model a flowing process, so any kind of treatment process or chemical or oil and gas process as well. And then this shows some selected industrial applications for OLI solutions. So in the upstream area, we can model SAGD, steam injection, as well as carbon capture, transportation, and storage. In chemicals, our software is used for digitalization, as well as pilot plant design, and looking at distillation or hydrolysis reactions. In metals and mining, we've modeled potash production, as well as rare earth element extraction and recovery, and lithium extraction from multiple sources. On the power side, we've been used to model flue gas desulfurization scrubbers. And then on water treatment, there's been a host of applications, looking at desalination with membranes, reverse osmosis, as well as evaporation, zero liquid discharge, and then also cooling tower water reuse and recovery. We do have some unique and differentiated chemistries in the OLI database. I'll just touch on a couple of these. Oil and gas, we cover glycol and methanol, as well as H2S scavengers. On oil and gas, we cover the amine and amine HCl chemistry, as well as HF. Metals and mining, we talked about lithium. We can also do potash, as well as heavy metal mining. Power generation, we can do borates as a part of nuclear power generation. And then on water treatment, we've got a host of pollutants, more conventional pollutants, including arsenic, antimony, selenium, mercury. We've recently added humic sulfate substances, which is important for a surface water source. We can also do struvite, which is an issue in a lot of municipal wastewater treatment plants. So our solutions are able to optimize process design and operations, so it can result in greater operational efficiency by a more efficient process design, or better operational efficiency resulting in higher operating margins. It can reduce the operational risk by reducing the amount of equipment and process downtime or proactive shutdowns, and then it can also increase engineering productivity. So next, I'll get into industrial water treatment drivers. So this section is a little bit of background on industrial water. So this graphic came from USGS in 2015. They looked at the source as well as the use of water in the United States, and these are shown in million gallons a day. So 237,000 million gallons a day of surface water withdrawn for a variety of uses. I just point out the thermoelectric power is about half of that use, and a lot of that is a result of the use for cooling. Industrial water use and mining would be what we're talking about today as far as industrial water treatment, and the numbers are relatively small, but it tends to be a very complex stream to treat, and I'll get into some reasons why that is. So what is industrial water? It's typically divided into categories. Power, and it's primarily coal-fired power because the water wastewater treatment tends to be fairly complex to treat. Mining, there's chemicals and petrochemicals, both upstream and downstream oil and gas, manufacturing, and food and beverage. And so in all these industries, water is used in the process, and it contacts either raw materials or products, or it's used in the production process. And contacts that, pollutants are transferred, and then that wastewater has to be treated before it's discharged. And it can either be discharged to a surface water or to a publicly owned treatment works. And one of the differences is that each of the wastewater generated for each of these industries, is dramatically different. And so when you're looking at industrial water treatment, you need to have expertise in one of those industries. And then even within an industry, the wastewater characteristics can vary depending on the production process used. So really, industrial water is highly tied to the production process and the chemical production process. So in terms of a permitting process, a direct discharge permit is driven by EPA or state, and the limits are going to be based on surface water quality standards, which can either be set at the state level or the federal level. And then EPA also has set effluent limitation guidelines by industry category. And so these are established by EPA. They're a technology-based limit, and they would apply to any plant that's subject to it, or any production area that's subject to it would be the same regardless of where it's located. Whereas surface water quality standards are dependent on the location and the receiving stream, so they can vary significantly location to location. Indirect discharge would be one that's sent to a publicly owned treatment works, and those limits are going to be based on the POTW permit, so they're going to have a direct discharge permit, and they'll then roll those limits up to their industrial users. There can also be effluent limitation guidelines that apply to an indirect discharger, and then the POTW also has the ability to protect their treatment processes, so they really have a lot of leeway in terms of what limits they set, because they need to have a well-operated facility that complies with their direct discharge or NPDES permit. And so what are conventional pollutants? So I'll get into emerging pollutants or emerging contaminants next. But as far as conventional pollutants, these are well understood. So we know what the health effects and the ecological effects are for these pollutants. They're typically regulated at the state and the federal level in most cases. And these would include parameters like biochemical oxygen demand, or total suspended solids, or heavy metals like copper, mercury, cadmium, zinc, those kind of metals. So emerging contaminants are those pollutants that have been detected in water bodies. They may cause ecological or human health impacts, but it's not, the exact impacts are not known, and they're typically not regulated. It can include new compounds or compounds that are detected as a result of better analytical techniques. And generally with these emerging contaminants, they're not removed in a conventional wastewater treatment plant. And that's what this graphic here is showing, where you have hospitals, industry, households, all discharging to a wastewater treatment plant. That plant goes to a surface water receiving stream, and then that receiving stream may be used for as a drinking water source. And so then those pollutants end up passing through the drinking water plant as well and end up in drinking water. And that leads into more details on emerging contaminants and PFAS. PFAS are per- and polyfluoroalkyl substances, and I'll get into more details on what exactly PFAS are. But some other emerging contaminants are 1,4-dioxane, pharmaceuticals, natural and synthetic hormones, food additives, cyanotoxics, which would be like cyanobacteria or toxic algae, and then also nanoparticles. Being in the Houston area, you've probably heard about microplastics, and that would be considered an emerging contaminant, because it's raised a level of concern, but the exact impact of those nanoparticles are not known at this time. So this is a history of PFAS, and it also includes some of the kind of high-profile PFAS compounds. So PTFE or Teflon was developed in the 30s. It was used with coatings in the 40s, and then waterproof fabrics in the 70s. PFOS is one of the kind of the major PFAS. It began production in the 40s and then was used in stain-resistant coatings as well as firefighting foam. PFOA is another one of the big, PFOA and PFOS are probably the most studied PFAS compounds, and PFOA was used in protective coatings, up until both PFOS and PFOA through the 90s. And then in the 2000s, the U.S. agreed to reduce PFOS, PFOA, PFNA, and then some other PFAS. And then the other thing that happened in the 2000s was that the analytical techniques were improved. So these analysis methods were able to get down to nanogram per liter or part per trillion levels of these compounds. So it was more discovered that these compounds were in a lot of drinking waters, and it started to cause some concern. So as far as PFAS and what they are, they can either be non-polymers or polymers. For the most part, for water, we're focused on the non-polymers. And there's perfluoroalkyl substances, and those are PFAS compounds which are fully fluorinated. And then there's polyfluoroalkyl substances. Those are not fully fluorinated, and they can undergo transformations through treatment plants and other processes. So we mainly are focused on the perfluoroalkyl substances, and within that group, there's either what these molecules are a carbon chain or a carbon backbone with fluoride substituting for hydrogens on each of the carbons. So if it's fully fluorinated, then it's going to have all fluorides and no hydrogen. And then it's either got a carboxylic acid group or a sulfonate group. And that's how these are categorized and considered for treatment and in other areas. So PFOS and PFOA have gained early attention. EPA has set a health advisory level for the sum of PFOS and PFOA in drinking water at 70 parts per trillion. So there's some other PFAS compounds that are gaining more attention that are shown here in the orange and the purple. The fluorotolometers, those are polyfluoroalkyl substances. Those are gaining more attention, and then it's expected that other PFAS will gain attention in the future. So, and as PFOS and PFOA have been phased out, the manufacturers have developed substitute compounds which will fall into some of these other categories. So as these compounds are developed, then we have to study them and look at how we would treat them, look at the health effects, and that kind of thing. So PFAS are a large class of anthropogenic compounds, over 5,000. The commercial methods detect only a fraction of these compounds. The tail contains a carbon chain with fluorine substituting some of the hydrogens on the chain, and that's the hydrophobic end. The head contains a polar functional group, and that's a hydrophilic or water-loving end, and that end is either a carboxylic or sulfonic acid. And so because of this, it has very unique surface active properties, and that's why it's been used in so many applications. So, very early on, it was used in nonstick cookware, stain-resistant products, firefighting foams, photography, shampoo, as well as other healthcare products. And that's one of the issues with sampling for PFAS is the samplers have to be aware of what they've touched that day. And so if you were to go sample for PFAS, you can't use sunscreen, bug spray, you can't wear makeup. There's just a whole host of things you can't do because these compounds are really everywhere. And when you're looking at analytical methods that can detect down to a nanogram per liter, then inadvertent contamination is a real concern. And as far as some of the industries that used PFAS, it was historically used, PFOS or PFOS was used as a fume suppressant in chrome plating. So with the manufacturer, it's found where facilities that manufactured military vehicles, construction equipment, airplanes, aerospace equipment. It was also used in the manufacture of fluorinated pesticides and herbicides. It's been used in firefighting foam. So, you know, a few industries are noted here as far as manufacture or testing of firefighting pumps and equipment, airports where they've had a release, you know, maybe had a fire and then had used firefighting foams, and then that contaminates groundwater. A lot of airports and counties and other areas have firefighting training facilities and will have historically used PFAS at those facilities. And then another big source is landfill leachate, and that's because a lot of these compounds have been used in materials that end up in a landfill. So historically, PFAS was used to make carpet stain resistant. So then, you know, you take the carpet out of your home, it goes to the landfill. Similarly, it's been used with fast food containers to make them oil or stain resistant. And so it's typically present in landfill leachate. A lot of landfill leachate goes to a municipal wastewater treatment plant. So PFAS has been found in a lot of municipal wastewater treatment plant effluents. As far as PFAS presence in drinking water, this is a map of the U.S. The blue shows where PFAS has been detected in drinking water. And then on the right side, the different sites are classified. So, you know, many of the sites are either industrial, military, AFFF, airport, or wastewater treatment plant. And the presence of PFAS in drinking water really kind of follows the regulation as well. So EPA has not set a maximum contaminant level for PFAS, but some states are going ahead with that. And so what you see is a lot of blue area in California. California is regulating PFAS in drinking water. The Northeast, there are many states in the Northeast that are regulating PFAS in drinking water. Michigan and Wisconsin show quite a bit of blue. There's been a lot of manufacturing activities in those states, and they're regulating PFAS. And even in Michigan, PFAS has been detected in surface waters, and there are cities that are treating for PFAS, like the city of Ann Arbor removes PFAS from their drinking water. You know, and they are doing that really just as a service to their users. They're not required to treat, but they're concerned about there being any PFAS there, so they're treating. And then, you know, I'm from Atlanta, from Georgia, and what you see is a blue area in the northwest corner of the state. That's Dalton, Georgia, which has historically been a center for carpet manufacturing. So you see PFAS there. The Dalton utility, they treat for PFAS. And then I've even heard that PFAS has been detected 100 miles downstream of Dalton. So it just doesn't degrade. And so it can really travel far from where it originates. And then you also see it around military, Department of Defense facilities. That's kind of in the mid part of the state. That's where Robins Air Force Base is. There's been PFAS detected there. You know, similarly, like Eastern North Carolina, there's a lot of military facilities and manufacturing facilities. So you see it across most of Eastern North Carolina. So as far as NPDES and PFAS, states will use the NPDES, or National Pollutant Discharge Elimination System, to control discharges from point sources containing PFAS. So the effluent and receiving water limitations would be established similar to other pollutants. And EPA is stated in their action plan that they are going to evaluate whether water quality standards are warranted for PFOS and PFOA by 2021. But we're almost into the fourth quarter, so they obviously aren't going to make 2021, but they have announced that. However, some states have gone ahead with regulating PFAS, but currently Michigan's the only state with a PFAS water quality standard. I show here on the slide a few states other than Michigan. These other states have set action levels to where it might trigger a permittee to look at treatment or possibly to do something. But Michigan has passed water quality standards, which means those limits can be incorporated into discharge permits. And for PFOS, that's 11 parts per trillion, and then PFOA is 420 parts per trillion. And PFOS is bioaccumulative, so Michigan will not allow credit for dilution. So if a discharger had PFOS in their wastewater, they would have to meet that 11 parts per trillion at the point of discharge, which is pretty low. I mean, when I first started doing work in this area a few years ago, about the best detection level we could get in an industrial effluent was 10 parts per trillion. So that's just above the detection level. Now the analytical methods have gotten better, and you can typically get down in a single digit, but that's still pretty low to try and achieve compliance with consistently. POTWs in Michigan have started regulating PFAS, and it really varies by the POTW. Great Lakes Water Authority, which is in the Detroit area, they have a renewed NPDES permit that includes limits for both PFOA and for PFOS. So they're requiring PFAS monitoring for industrial users, and then if it's detected above a certain level, then they require that user to write a best management plan, and then typically they have, in some cases, have required treatment or have just eliminated the discharge. And in a case where there was a indirect discharger to their facility, and they couldn't install treatment within the time that the POTW wanted it, and so they just cut off the discharge. There's another POTW in the Detroit area, Ypsilanti County Utility Authority. They are also requiring monitoring and are requiring a pollutant reduction plan, which is similar to a best management practice, best management plan. But their current NPDES permit expires this year, so they have not actually received a permit with PFAS limits. But once they do, then that may require some of their indirect dischargers to install treatment or look for another discharge possibility. Another way that PFAS may be regulated is through effluent limitations and guidelines. EPA has announced a multi-industry detailed study, and so they're very early in the process, and they're looking at certain industry categories. So PFAS manufacturers, pulp and paper manufacturers. Historically PFAS has been used to coat paper to make it oil or stain resistant. They're also looking at textile and carpet manufacturers because of the use to make it oil and stain resistant. Airports are another big source because of the use of firefighting foam, and then also metal finishers because of the use of PFOS as a fume suppressant. And they're really just doing this through outreach. So these manufacturers are not required to submit information, but they are looking for information like what PFAS compounds have been discharged, the concentrations, whether they're treating for it, and the flow rates. And so what may come out of this study isn't more study, but eventually they may end up setting a effluent limitation guideline for PFAS for specific industries. And then that would mean that every manufacturer within that category would have a limit for PFAS, a technology-based limit that they would have to comply with. And that would be in addition to a surface water or receiving stream standard. So now I'll get into PFAS treatment. This slide, it's taken from a Michigan Department of Environmental Quality publication, but it shows the cycle, the current, at least, environmental cycle for PFAS. So PFAS can result from a factory. There could also be a contamination site, and PFAS gets into a water, or maybe there's a discharge from a factory to a wastewater treatment plant. Some of the PFAS compounds can absorb the biosolids in the wastewater treatment plant, and if those biosolids are land applied, then PFAS can get into crops or surface water through that mechanism. And then the PFAS can also be present in the discharge from the wastewater treatment plant, which would go to an aquifer, and then that water could then be used by a public utility to provide drinking water. PFAS can also come from homes and then also be discharged to the wastewater treatment plant.
This graphic shows PFAS removal efficiencies for typical water treatment methods. The cells shaded yellow indicate less than 10% removal. The green
Sorry.
cells are 10 to 9.
Okay.
This
let's
graphic shows PFAS. This graphic shows PFAS
I reused
removal.
a slide. I reused a slide from another presentation, and it was one done during COVID, and so it's got, I didn't realize it's got sound with it, so. Change the setting. So maybe. It's gonna take a second to pull back up, and maybe I'll just talk through it too. So the slide.
This graphic shows PFAS removal efficiencies for typical water treatment methods. The cells shaded yellow indicate less than 10% removal. The green cells.
I'll talk through that. So, I guess I could let y'all listen to me too. That would be an option. So the slide shows typical processes used in a wastewater treatment plant and indicates which processes are effective. And so typical processes like filtration or coagulation are not effective. The ones that are affected include activated carbon and ion exchange. And what that chart shows is on the left side, the PFAS compounds are in order of the number of carbons in the molecule. And so the top of the chart would be the shortest chain PFAS at 4 carbons, and then the bottom would be the longest chain at 9 carbons. And so what you see is that it's harder to treat, that like GAC and ion exchange are less effective on the shorter chain compounds and more effective on the longer chain compounds. And then, but our reverse osmosis is effective as well. You know, with any of those treatments, you're really just transferring the PFAS from one media to the next. And so what I'll get into a little bit more detail on ion exchange and activated carbon. So with ion exchange, you have a dual removal mechanism because of the two different ends of the PFAS the PFAS chain. So you'll get ion exchange at the on the end that's anionic, and then you can also get some adsorption. So it tends to be you know, an effective treatment, but generally more so with the longer chain compounds. One thing with ion exchange is you do have to be concerned with co-contaminants. So other ions like nitrate or sulfate are going to compete for those anion exchange sites and will really typically drive the resin usage, because with PFAS, most of the time we're looking at nanogram or part per trillion levels, where these anions like sulfate or nitrate can be there in milligram per liter, or even 10s or 20s or more. Another co-contaminant is organic fouling. So that fouling, that organics can foul the resin and reduce the life of the resin. With ion exchange, it can either be single use or regenerable. If it's regenerable, it's typically done on site, and then you end up with a concentrated stream of PFAS that then you have to manage further. With activated carbon, it's typically, oh wait, I was going to point out this, the graph, both of these graphs are for an actual water that was tested by a firm, GHD. It's an engineering firm with a treatability laboratory, and that's typically what's needed. Well, it's not wanting to go back. But with both ion exchange and with activated carbon, it's more effective on the longer chains. And so both of these graphs are color-coded, so the shortest chain is red, then orange, yellow, basically in order of the rainbow. And so what you see is these shorter chains, the PFBA, which is a C4, the red line, the orange line is a C5. You see those break through first. And so that, you know, currently this water, the site was in Michigan. Michigan's regulated PFOS, and so, you know, we're mainly concerned about PFOS breakthrough. But as Michigan's looking at adding more PFAS compounds as far as a drinking water standard, and so the expectation is if they set a drinking water standard, say for PFP-EA, then likely they're eventually going to set a surface water quality standard. So, understanding which PFAS you need to treat for is important, and then also understanding the time to breakthrough is important as well. Similar to ion exchange, co-contaminants can affect media usage, and total organic carbon concentration can really drive carbon usage. So with total organic carbon concentrations are typically in the milligram per liter, maybe up to 100 milligram per liter, and so those can really drive usage. Incineration can be used to destroy PFAS and regenerate the media. The regenerated carbon may be less effective. There have been some studies that show it's less effective, although many of the manufacturers are trying to improve the carbon so that it's comparable to virgin carbon. Most of the manufacturers only have a few facilities in the U.S. which incinerate carbon and regenerate it, and so transportation costs can be a concern. And then also some suppliers will limit the PFAS loading on the media for regeneration. So it's not, not a guarantee that you're going to be able to regenerate your carbon, which, that would cause concerns both with carbon and with ion exchange. If that media were to go to a landfill, you wouldn't want the PFAS to leach back out and go through the cycle again. Membrane treatment has also been done for PFAS. Both reverse osmosis and nanofiltration are effective in rejecting PFAS. There are limited full-scale installations. And currently PFAS is such a new compound that a lot of the manufacturers are developing performance criteria in terms of the rejection rate, but a lot of those criteria are not publicly available currently. And some of them are, really kind of holding them close because it's somewhat proprietary. Similar to GAC and ion exchange, you're concentrating the PFAS, which is going to require further treatment or stabilization. It can reduce the size of the PFAS removal system, and I've seen it used in some drinking water plants with a relatively large flow. So it can, by concentrating the PFAS stream, then your PFAS removal technology is much smaller. There are a lot of developing PFAS treatment technologies. There's a lot of research going on in this area. One area is adsorbents. There's a proprietary compound called Rembine, which is a mixture of clay, powdered activated carbon, and aluminum hydroxide. There's a zeolite clay adsorption media that's also been used. I'm showing data here for Cyclopure, which is a dextrose-based media. This was some bench testing that they did on the same water that I showed on the previous two slides for activated carbon and ion exchange. And similar, you see the shorter change breakthrough, so that would be the red, yellow, and orange lines. But one thing they look at it on a specific throughput, so this is in terms of liters treated per kilogram of media, and compared to the activated carbon, this dextrose-based media was able to absorb 25 times the PFAS, which is significant. Now, it is a developing technology, and they have pilot tested it, but they don't have any full-scale installations. And they've also developed a destruction technology that's based on a ball milling technique. Claristech is another developing media. Their media they produce the media with a certain size to absorb the PFAS. They're still in a bench testing. I don't think they've done any pilot testing. And then there's a lot of work ongoing with plasma. There's several universities in the United States that are researching plasma for PFAS destruction, and then also electrochemical oxidation. So possibly some more techniques to come, and that's really the objective is really to find a destructive technology so that we can break up that molecule and not get it out of the whole environmental cycle. So now I will move into a section on simulation. and talk some about what we can do, what OLI can do as far as industrial water simulation. We've got a lot of established chemistries, heavy metals, mercury, copper, and zinc. Oxyanions can be very difficult to treat, which would include both selenium and arsenic, and we can model treatment of those anions. We can do scale prediction. We can also model scale inhibitors and are enhancing our technology around scale inhibition. We can do most of the major processes for water treatment, so precipitation, which would be like mixing and clarification, do softening, ion exchange, evaporation, and then looking at a host of source waters from brines, and looking at brine intensification or brine valorization and recovering valuable elements from brine, as well as flue gas desulfurization, scrubber blowdown. As far as emerging capabilities, we recently have added cadmium to our chemistry database, as well as lithium and rare earth elements. We've also added reverse osmosis, and then have also developed some cloud apps and an optimizer tool. And I'll get into some examples of these in a few slides. So PFAS is one that we can't do currently, but are considering adding it. Some of the challenges with it is that there are over 5,000 compounds, and only, depending on the analytical method, there's only 20 to 100 that can be analyzed for. Another challenge with PFAS is that the conventional treatment methods, so activated carbon and ion exchange, are both dynamic processes, and we would need a dynamic simulator as opposed to a steady state simulator. Another challenge is the regulatory status. So while certain states have passed maximum contaminant levels, one state's passed a surface water quality standard, it's unclear what other states are going to do, and unclear what EPA will do. One solution or one way to model it is to group the behavior according to the molecular characteristics. So we know that the shorter chains behave a certain way, or more difficult to treat. Some are more volatile than others, and then the performance or treatment can also typically follows whether there's either a sulfonic or a carbonic functional group. So something that we're still considering for addition to our chemistry database. One thing that I've used it for a lot is with metals precipitation. And in this slide on the left, I show a literature precipitation curve. So what you see is pH on the x-axis, and then the solubility on the y-axis. And these are used to evaluate what pH you need to run a treatment process to precipitate these metals. And you can see they all have kind of a nice parabolic curve, and the pH may vary from 9 to 9.5, and that's what those the vertical lines are. So lead might be 9.5, that's the pink line, zinc somewhere between 9 and 9.5, and then copper down at 9. And what I was looking at it was a facility that processed and recycled aluminum and had an on-site landfill, and this was leachate from their landfill. And so it was high in dissolved solids, so high ionic strength, and also high ammonia. And so what you see is the model predicted precipitation curves on the right that look vastly different from the literature curve. And so this really shows, our strength is simulation and predicting solids formation in high ionic strength solutions. And many times with the literature curves, you don't know the background water chemistry, and many times it's clean water, so it may not be representative of your water chemistry. And so what we see on the right is that, so copper was the main metal that we were looking at, which is the blue line, and this is showing the copper in the solid form. And so we needed to get up to a pH of 12 to fully precipitate the copper. And what you see on the EPA curve is it doesn't even go to 12. And so, if we hadn't run the model, then we would not have recommended testing at a pH of 12 in the lab. And so why are these different? This is another graph from the model, And this shows the copper, the solid copper is shown in the orange line. And these other compounds are copper ammonia complexes. And so the copper ammonia, soluble complexes. And so that's why it was so hard to precipitate copper. It wasn't precipitating until we got up to a pH of 12. When we got up to 12, all those copper ammonia complexes disappeared, and we were able to precipitate copper. You know, this was a pretty high total dissolved solid stream. It had 7% TDS, and the ammonia was over 1,000. But, you know, this really, the model allowed us to identify a feasible solution, focus the bench testing, and reduce cost for the bench testing and operation of the facility. Sorry, jumped ahead. So those previous curves were generated from OLI Studio, which is a single point equilibrium analysis. This example is from OLI flow sheet and is an example of concentrating seawater by thermal evaporation. And all the boxes that are shown are customizable, so you can look at, you know, what are the characteristics of the solids that come out of the evaporator, what's the liquid, how much vapor is created, and you can look at also variations. So if you were to modify, you know, just the pH on the influent, how does that affect solids formed? We've also recently developed a cloud API, which allows a user to take a flow sheet, so like something like a flow sheet that was shown on the previous slide, and upload it to the cloud, so that then if you had users that did not want to deal with like creating a flow sheet or build it from scratch, or maybe they have a process that's used in many different applications, an app, this cloud API can be used where it sits in the cloud. You can change the input parameters, the process parameters, and run it. You know, it's quick, and it sits in the cloud, so you don't have to have a license to OLI on each desktop. And this is another evaporation example. We've set up an input screen here to add the water quality and then certain process parameters. And then the output screen is shown next. You know, this is all customizable. So in this case, we're looking at the solids composition. So that's a concern in the brine, but it will show the content of the blowdown, or the flow rate of the blowdown, the temperature, heat exchanger duty, you know, any kind of parameter that the model calculates can be shown on these screens. So it could also be an operations tool as well. So if there was an operator in the field that had varying, say that the composition of the feed water was changing over time, and they wanted to understand how that would impact the blowdown quality or the temperature, then this would be an easy tool for them to change that quality, input quality, or, you know, like in this case, we were using waste heat. If that temperature of the waste heat were to change, then you could look at how does that affect the blowdown quality or quantity. I believe that is my last technical slide. I did want to put in a plug. OLI is sponsoring an AICHE webinar in October 20th on carbon capture, transport, and sequestration. So if you're interested in that, I'm showing the link here. I'm happy to provide the slides later. If anybody's interested in the carbon capture seminar, my colleague AJ Gerbino will be leading that. And then if, for more info on OLI, there's a variety of contacts here. And then we also have a booth in the exhibit hall as well, if you're welcome to come by and talk to us, or after today. And I'm happy to take questions now if there are any.
So Ramanand sends his apologies. He had a priority, his daughter's birthday party, and I'm sure anyone with children will understand. So he nominated me as a past chair. Actually, Tom, you take priority here. You should be up here, or maybe Vic. But anyway, he nominated me to take over and help wrap this up. So anyway, first of all, questions for Kristen. Let me come to you with the mic.
Thanks for an outstanding seminar about an important set of problems in environmental engineering and chemistry. I had a question, because these are low concentrations we're working with. You have mentioned using ozone. Have you tried hydrogen peroxide and Fenton's reagent?
Yes, yeah, that's a very good question. When I first started working in this area, the thought was that possibly could we get it through advanced oxidation processes, and there are some papers on that. It takes fairly extreme conditions, so like 100 degrees C and 8 hours exposure to the oxidant. So nobody so far has developed a feasible process. And I was actually part of a pilot test for an advanced oxidation process, which used UV and peroxide. And the supplier of that equipment, was aware of Teflon being a possible source of PFAS, but they didn't think about PVDF. And so they had these PVDF nozzles in the ozone distribution system, and so that pilot actually created PFAS. So it's definitely a difficult process, and so far no advanced oxidation process has been found that's feasible, at least at a full scale level.
Thanks very much.
Thanks, Vic. Thanks, Kristen. Any other questions? Oh, one up here. Mark.
Yes, in one of your earlier slides, you'd mentioned that some entities are looking at using reverse osmosis for PFAS removal. How are they intending on handling the reject stream?
Yeah, that's a very good question. I know of a municipality in Alabama that's using RO, and then they're treating the reject with activated carbon. So you do still need some other, still need a PFAS treatment. Mm-hmm.
Other questions? Okay.
Thank you for the presentation. I have a question regarding the discrepancies of the simulation versus the real data. And I think I wanted to make a comment. Nowadays, many engineers, many professionals tend to believe that the simulation of the newest packages are excellent. So I wonder if you have some additional insights about where to be cautious, because people take this as a real thing before being validated.
So the question is where to...
Getting your comments regarding what the expectations of a simulation package versus the real thing.
Yeah, that's a good question. I may rely on one of my OLI colleagues that are here. I've been with OLI for about 8 weeks. I will say I've been using the software for 15 years, so I know a lot about the application of it for water treatment, but as far as the software and the accuracy.
So I think the question was about making sure that you understand the results and how you're going to apply them, maybe possibly as one question. I mean, the second question possibly is about how do I trust the predictions from the software? So OLI has been around for 50 years as a simulation company. We use first principles data, so if you're looking at any particular system, you can look at the fundamental data upon which the predictions are based. So it's good to understand not only where you're operating, but what your limitations are in terms of your concentration, in terms of the interaction with all the other components in the system. So for any particular system that you're looking at, so the metals one that Kristen was showing would be a good example. So if you want to understand the specifics and the actual literature data upon which the parameters have been developed, that's a good place to start to make sure that you understand the fundamental, I guess, matching of your model to what you're going to see in person or what you're going to see in the field. So it's also good to understand, so that's kind of where you start. And then from there, you need to understand what you're trying to predict and how far outside of that boundary that you're going to be.
Thank you, Jordan.
Yeah, I think that my comment is trying to go beyond of what we are here, many mature professionals, is trying to coach us young professionals, right? That whenever you have to deal with part per trillion, part per billion, they have to check many things before they go and make a recommendation to their employers. And I guess many people who have been around, like in the field, now with all these new computer programs, they believe that they have the answer. In reality, the experience and all the fundamentals that you have to put in place. And that's what I wanted to derive this comment, because clearly I have the opportunity to use OLI back in my times in the chemical companies, but clearly it's PPTs, PPBs are an issue for the young professionals to understand the implication of use a program and just get the fundamentals. Thank you.
Thank you.
Any other questions or comments?
Work Kristen and Jordan here, and it's a very good point that's been brought by Antonio. Just this past couple of weeks, I had that question where a client was pitting other softwares, well-known softwares, against ours on just a simple desublimation of a salt, and trying to understand, okay, if I'm making an operational change based on what the software is telling me to do, how do I trust what the software is telling me to do, right? And I think it goes back to the fundamental question is, where's this data coming from? You know, something that we do, and I'm sure the companies do as well, is that we provide validation plots. Here's all the data that we used for our thermodynamical regressions. You know, something that's different from what we do from other process simulators is that the thermodynamic models that we only have 3. Right? So one of the things that you're looking for when you're doing process simulation is, okay, well, I have a list of 20 equation of states, activity coefficient models, binary interaction parameters. Which one do I use? Right? With us, it's a little simpler, but because it's a combination of many of those things. So one of the things that we're very transparent about is, here's all the data that we found. All the data that we found about this chemical system matches with each other, okay, from different sources. And here's our regression based on those data points that we found. And we can guarantee that it's going to match that regression based on the limits of that data, right? Anything outside that data, well, you're extrapolating. It's not very, you're guessing at that point, right? But that's something that, you know, as a young engineer, you know, maybe I like to consider myself young, but I don't know if I'm there still. Yeah, it's going back to the data. It's going back to you know, whoever's providing that to you and asking, well, can you show me what you're getting this from? Because I'm going to make an operational change. I'm going to turn on that wash water. I'm trying to save wash water. If I turn it down, will I foul my entire system, or will I still be reliable, right?
Thanks a lot. Any more questions? Hearing none, and since it's after 8 o'clock, I guess it's time to wrap this up. I will mention before I close, I still see dessert at the back there. And I know some of us never got around to getting it first time around, but oh, so were you going to take it all, Trevor? Were you going to take it all? Oh, you're right there. Yeah. So if anyone does want to grab some dessert, there is some back there. So, Kristen, thank you so much. That was a fascinating presentation on what you're doing at OLI and the PFAS information. Excuse me, I'm losing my mask here. Oh. But anyway, a gift for you. Appreciate it. Thank you very much. Okay, dessert and